So moving on to question 3b, we have current source and resistor in series with the current source, in series with another resistor, and they all become in parallel. And then we have a diode, and that diode will go up there, and we have another current source just here. And resistor, and another resistor, there, and we have a diode here, and a diode, or rather this diode here connects to that point there, and this is 2K. And that's 2K, that's 10K, and that's 1K. And this is 20 milliamps, and this is 10 milliamps. So the question asks, or the question says, the circuits in figure 3 are more complicated than those in figure 1. Identify the conduction state of the diodes and calculate either the reverse bias voltage or the forward bias current as appropriate. Assume that the diodes perfectly block current flow for all anode to cathode voltages less than 0.7 volts, the reverse bias state, and conduct perfectly if the circuit tries to make the anode to cathode voltage greater than 0.7. Note, in circuits with two diodes, there are in principle 4 possible combinations of conduction state. Start by making a guess for both diodes and proceed as for a single diode to find out whether your guesses were right. So 3 part A is not done because I haven't given an answer for it in the sheet, because this is one of those questions where you have to make a judgment as to whether it's conducting or not. And I don't want to give away the answer because that will tell you what that judgment should be. So we'll start with 3b, and we'll have to say first of all that neither diode is conducting. So we can get rid of the diode there, and get rid of that diode there. So we've got rid of our diodes, and now we need to work out what VAC is, and I'll call this one VAC1, and I'll call this one VAC2. And we can say, well, for VAC1, to get the anode voltage, I really need the voltage across this 2K resistor. And to get the cathode voltage, this would be the anode and that would be the cathode, because the diode faces up the page in the question. To get the cathode voltage, I need the voltage across all this lot. So for this one here, so I'll call that VA1 if you like. VA1 is 20 milliamps times 2 kiloohms, because there's a loop here, and there is no possibility of current in this part of the circuit getting over to this part of the circuit, and no possibility of current in this part of the circuit getting to this part of the circuit, because there are no connections. Despite the fact there are wires in the middle, none of them are actually complete, so there's no method for current flow between the two halves. So we can say 20 milliamps times 2 kiloohms is 40 volts, and this is on the anode. And we can do the same for here, and we'll call this VC1. And VC1 is equal to, I've got 10 milliamps going up there, along there, down there, down there, down there, round there, and back up there, in this loop. So the 10 milliamps passes through both resistors. So I'll add them up and I'll get 11k, which is resistance there to there, the 10 plus the 1. So we'll have 10 milliamps times 1K plus 10K, which is 110 volts. Fine. Only thing is, this is our anode. So our anode is at 40 and our cathode is at 110. So if we want to do V anode to cathode, we'll have to do or equals 40 minus 110. Well, that's minus 70. Which is not plus 0.7. So this diode is switched off. And we can have a look at VOC2 as well. So first thing to say is D1 is off if D2 is off. So then we can have a look at VOC2, and we can say, well, this point here is the cathode for diode number 2, and really it's actually the same as the voltage across here. That voltage there to there is the voltage on this wire, which is the cathode, so we'll call this VC2. And the voltage on the anode of D2 is the same as the voltage across the 10K resistor, this 10K resistor. So we'll call that VA2. In which case we can say that VC2 is equal to 20 milliamps multiplied by 2K plus 2K, which will give us 80 volts. And we can say, sorry, that's VC2. And this is VA2 is I times R, which is 10 milliamps from here, around there, multiplied by 10K. And that's 100 volts. And VA2 is the more positive in this case than VC2. So VA to C is 100 minus 80 volts, which is 20 volts. So D2 is conducting. If D1 is off, or not conducting. I could say not conducting would be better, but there isn't enough space, so off. So now we've got to reanalyse the circuit with D2 conducting, and we need to check that when we analyse it in that state, that it doesn't change the voltages around D1 to make it conducting as well. So that's what we'll do next. Alright. So we've got D2 is conducting if D1 is not conducting, and the direction of the diode is up the page, so we've got a 0.7 volt source there. And the easiest way by far to do this is probably by loops, because it'll take quite a while by superposition. There's 3 to do. So, to maintain consistency, I'm going to talk through the answer that's on the sheet, because if I give 2 different answers, things will get a bit messy. So we have some loops, and the loops are I2 here, and we have a loop called ID here, and we have a loop called I1 just there. You can choose the loops any way you like, and if you wanted to, you could have a super loop, which is round there like that. That'd be fine. And you only need 3 loops for this though, so you can choose them however you wish. And you don't necessarily have to pick the directions that are picked here. You could say ID goes the other way if you want to. That would be fine. In fact, the diode current, we know that the diode this is the anode of the diode, and this is the cathode of the diode. So we should expect, given that we've decided D2 is conducting if D1 isn't, which is the situation we're now looking at, we should know that we're expecting a current to be going up the page, because if it's not, that means that there's something wrong with what we've said over here. So we'll bear that in mind, and we'll call it ID. What else do we know? We know that we've got that this is VA1 and this is VC1, because that point runs round to just there. So we can say that I2 has to be minus 20 milliamps. And we know that because the current that travels in this branch is 20 milliamps in this branch through the current source. So the current source is in the middle of this branch, and we know the current source has got 20 milliamps. And the other thing we know, which often trips people up, is that the only current that's a loop, so these are our loop currents, the only loop current that flows in this branch is I2. So that must mean that I2 completely describes the current in this branch. It's not the case that there's another branch over here where we've got 2 currents describing the current in this branch, 2 loop currents. If this circuit carried on, say there was some other stuff over here like this, I don't know, resistor maybe, and I said, oh well, there's another loop here called I3, then I'd have to say, well, the 20 milliamps is described by the sum of I2 and I3, but in this question there is no extra stuff over here, and I2 is the only loop current that describes this branch current here. So we can say that I2 is equal to minus 20 milliamps by inspection. You look at the circuit and you know the circuit theories and you go, this must be true, or this must be a fact anyway. And we know it's minus because we are saying that the loop current is doing that around the circuit, but we're saying the branch current is up the page, which is not down the page, so that's where the minus comes from. The other thing we can do is we can do the same for I1. We can say, well, I've got 10 milliamps going up here and around there like that, and I've also got I1 going around that way, so I1 completely describes the current in this branch here, and it must be the same as whatever the source is, so I1 must be 10 milliamps. loop analysis tends to work quite swiftly if you've got current sources, and node analysis tends to work quite swiftly if you've got voltage sources. If you've got a bit of both, then you have to make a judgment based on experience. So we can now say, write some equations down to describe what's going on in the circuit, and we can sum up the currents, or rather we can sum up the voltages around this current loop, ID. So we'll say that for this resistor and this resistor, tell you what, I'll redraw ID to show its pathway properly, because that will make everything a little bit clearer. So nothing's changing, I'm just redrawing the loop a bit more to follow the pathway that it actually flows. So we have ID takes this pathway and I2 takes this pathway. Which is the same as what we had there. So we've got I2 going like this, and ID going like this. And this red line here is this branch current only. I'll remove it for clarity. So we have in this 2K resistor and this 2K resistor, we're going to have ID flowing downwards and I2 flowing upwards, and we'll say that it will be ID minus I2, because we're essentially saying, looking at a voltage like that, multiplied by 2K. So this is the voltage across this resistor as a function of its value, resistance, and of the two currents that are flowing through it, plus ID minus I1 times 10K. Right, now let me deal with I1, because I didn't change that, did I? So nothing really is changing, I'm just redrawing these to make it a bit clearer as to what's going on. So this is I1. So we've got ID minus I1 times 10K, so we've got a voltage like that. And then we've got the 0.7 volts. Is that what we're doing next? No, we do that right at the end. Plus ID minus I2 times 2K. So this is this resistor here, and we're looking at that volt. So we've got ID minus I2 times the 2K gives us this voltage. And then we add the 0.7, so we've got 0.7 volts here as well. And if you look at these voltages around this loop, they all face the same way. Okay, these two appear not to face the same way as these two, but in fact they all face the same way, because the current flows down the page here and the current flows up the page here, because it's going around the loop. So if you were feeling really insane. You could put one of these arrows on backwards and you'd have to remember that one of these pluses would in fact become a minus. One of either that one or that one or that one would become a minus. But I'm not going to do that. I'm going to stick with the way it's done on the solution sheet. So we'll collect together the terms now by multiplying everything out, and we'll say that ID times 2k plus, minus rather, I2 times 2k plus ID times 10k minus I1 times 10k plus ID times 2k minus I2 times 2k plus 0.7. It's the same as the line above, just I've expanded all the brackets. And then we'll collect together the terms in ID. So we've got ID square bracket, 2k from there, I've got 10k from there, just here, so I've got this term I've done, that term I've done, I'm going to do this one next, plus 2k, that's all my terms in ID, and then I've got minus some terms in I2, but what I'd rather do is call this one plus, and then put a bracket in here, and say the first one's minus 2k, so I just did that term there, and then I'm going to do this one next because that's I2 as well, and that's minus, so minus 2k, and that's all the terms in I2, so I did that one. And then I'm going to do the terms in I1, which will be just the 10k. So I did that term there. And then I'm going to add the 0.7 on the end, which is that term there. So now I've got an expression for my currents, and I can insert some values because I know what I2 and I1 are. They're 20 and 10 milliamps. So I'm going to rewrite that there, and I'm going to go up the top because otherwise I run out of room. So I2 is minus 20 milliamps, and I1 is 10 milliamps. So we'll just transpose this up and insert the bits and collapse everything together. So we've got, by the way, this is all equal to 0. Has that gone missing from somewhere? It has. The reason it's all equal to 0 is because we've got volts times ohms, amps times ohms, which is volts, amps times ohms, which is volts, amps times ohms, which is volts, plus volts, and what we're really doing is summing up all the currents. And Kirchhoff's voltage loop law says that all the voltages around the loop have to sum up to 0, otherwise the energy is escaped. But that is what the law says, but under certain circumstances, which we won't cover in this course, you can make it a bit more flexible. But to do with inducing currents or voltages in circuits. But as far as this course is concerned, it's a law and it's fixed. So moving up here, we've got 10k plus 2k plus 2k is 14k. That's a multiplied by the way. And then we've got plus I2 times minus 4k plus I1 times minus 10k, so no change there, plus 0.7 is 0. So then we can say, well, we don't know what ID is, we're going to solve for that, but I do know what I2 is, it's minus 20 milliamps. So next thing to do would be to say ID times 14k plus minus 20 milliamps times minus 4k plus, now I1 is 10 milliamps, plus 0.7, 0. And then we can, all this stuff is now numbers. So we've got ID times 14k plus 20 times 4 is 80. And it's plus 80 because we've got minus times a minus is plus, so there's 80 there. Plus 10 times 10 is 100 and it's minus 100, so I'll make that minus 100. And then we've got plus 0.7 equals 0. Alright. So if you're wondering about where the two 40s come from in the sheet, they're in here because I added the two 2k resistors. Damn! Added the two 2k resistors to get the 4k. Right, so then we'll do a bit of shuffling around to get this in the right place. Ran out of space again. We'll say that ID times 14k is equal to minus 80 plus 100 minus 0.7. So all I've done is I've moved these three terms over to the other side, and then I'm going to divide through by the 14k to leave me with ID is equal to minus 80 plus 100 minus 0.7 divided by 14k. And that is, we do the minus 80 plus 100 minus 0.7, we'll get 19.3, upon 14 is 1.3786 milliamps. And it's milliamps because I've got kiloohms and volts. So that's the current we've got for ID. And this, even though we've been calculating the loop current, we don't have to worry about the difference between ID and ID, because ID loop current is the only current that flows in the diode. So these two must be equivalent to each other, which is why they've got the same letters. So then we need to worry about what happens in this situation to D1. Because we said D2 is conducting if D1 is off. That's fine. And now we've worked out how much current D2 has. It's 1.37 milliamps. So now we've got to think, well, if we've got this situation where D2 is conducting if D1 is off, we've got to go back and make sure that D1 really is off. Because if it isn't, we're going to have to either accept that we made a mistake or figure out what was going on. So we need to get rid of some of this stuff to make some space. So what we want to know now is what is this voltage? Sorry, what is this voltage here? Anode to cathode, VA1 minus VC1. Well, VA1 is 2 kiloohms times. Sorry, VA1 is 2 kiloohms. This one is that voltage there. 2k times ID minus I2. And we've got to remember, of course, that this is actually negative because this is I2 is minus 20 milliamps. somewhere up here. So we have VA1 is equal to ID times 2K, and it's this 2K resistor here, minus I2, which is, sorry, I've written it there, it's I2 times 2K, and that's 1.3, rubbed it off. It was 1.37 something, so I'm gonna put 1.38 because I've rubbed off the number. I don't know what it was. Milliamps times 2K minus I2 is minus 20 milliamps times 2K, and we're just into arithmetic territory now. So we'll do a calculator, and we'll do 1.38 times 2. Minus, so it's actually plus because there's two minuses, 20 times 2, which is 40, so 42.76 overall. So that's here, 42.76, and it's VA1 with respect to reference, and the reference is this lot. So then we've got to get the cathode voltage as well, and we can see that it's I1 times 1K plus I1 times 10K minus ID times 10K. Or if you don't see that, it's fine. When we write it out, we'll go through it a bit quicker, a bit slower. So we've got, we want to know this voltage here across this resistor and that resistor. So we can say, well, in this resistor we've got I1 only, so we'll say that VC1 is equal to I1 times 1K. And then in this resistor, we've got I1 in the 10K, and take away this current because it's going the wrong way as we're looking at it, because we want this voltage with the arrowhead up there. So this current and this voltage are facing the same way, which is not right, because this must dissipate power, so there must be a minus sign. Minus ID times 10K. So we'll run that through, and we've got I1 is 10 milliamps times 1K plus 10 milliamps times 10K minus 1.38 times 10K. That's that's 10 volts, that's 100 volts, and that's 13.8 volts. In which case we've got 110 minus there's 90 something. 10 plus 100 minus 13.8, 96.2. So here we've got 96.2 volts. So this is the anode of the diode. The diode is here, this way around. And this is the anode, which is at 42 volts, and this is the cathode, which is at 96. So the anode to cathode for D1 is 42.76, so anode voltage minus cathode voltage 96.2, which is clearly negative by about 40 something. 53.44. So, because this is not more than 0.7, we can say therefore D1 is not conducting, even when D2, sorry, not very good, even when D2 is conducting. Or if you don't fancy that, we can say not if, and. Because that's what this last bit has been about. It's making certain of that condition. Alrighty, so question 3 part C, the answer is not given because you have to make the assumptions about whether the diodes are or are not conducting, and I'm not going to give away the answer to that one because I don't want to ruin the opportunity that you've got to practice without knowing beforehand what's going to happen. Because when you walk into the example, you won't have had the opportunity to practice those questions beforehand. So let's get rid of this and we'll move on to question 4.